Hello everyone, my name is Andrea, and together with Samuel, we are going to talk about Rust-vmm and how is this project helping building laser-focused VMMs. So we will first look at VM-based isolation, what it means and where it's used. We are also going to look at what Rust-vmm is, and then we are going to do a dive deep into the project to really understand how is this project set up and how it helps in improving the modularity and security of virtual machine monitors. So the first thing is that recently, in the past few years, we saw that virtual machines are used more often to provide isolation for workloads. And the workloads are fairly different. So we've seen VM-based isolation being used in serverless, and we have here an example with AWS Lambda, but we've also seen it used with containers, with AWS Fargate, and open source projects such as Kata containers. And then we also saw some more general purpose workloads being isolated with virtual machines. And so because of this, we would like to really do a dive deep and understand what it means to isolate these workloads with virtual machines and what work is required behind the scenes. So if we take a really quick workload, let's say that you want to do some processing on some images that somebody uploads on social media. So what you will do, or what you can use, is you can use AWS Lambda for processing the event. And then AWS Lambda behind the scenes is using Firecracker to provide isolation for each workload. And now, again, behind the scenes, Firecracker, in order to be able to provide this isolation and actually have this workload run, it needs two central pieces, let's call it. So two central devices. It will need a block device, which essentially provides the storage. And then it will also need a network device for the communication, because it will need to fetch the image, for example. Now, on a different spectrum, so at the other end of the spectrum, we also have, let's say that we want to develop a game engine. And for this, we want to go the route of general purpose virtual machines. And so we are using Amazon EC2. Amazon EC2 is powered by AWS, by the AWS Nitro system. And for this particular workload, the central pieces are three devices. So we will need a block device for storage, again, network for communication, but also the difference here is the need for graphics, so GPUs. So how were these kind of virtual machine monitors or virtualization stacks built? They were built either from scratch, either from forks of existing projects, and they would all need to go and solve the same problem again and again. Because even though they run fairly different workloads and they have very different purposes, at some point it boils down to the same set of components. So we see that both of them can use block devices, network, and some have additions, some have devices that they don't need. So this is where actually Rust-vmm comes into play. And this is why Rust-vmm was born. So Rust-vmm was born in order to fill this need of providing virtualization components that can be reused for building laser-focused virtual machine monitors. These virtualization components are written in Rust, and they are called crates. This Rust-vmm project, it's open source. You can find it on GitHub under the Rust-vmm organization. Rust-vmm has been used in production since 2019 with Firecracker and Cloud Hypervisor, and it was purposely built for virtual machine monitors. So most of the use cases were around virtual machine monitors, also Alibaba Cloud Sandbox and InArcs. But then what we noticed in 2020 was an interesting shift where these Rust-vmm components were not only used in virtual machine monitors, but also in other applications. So here I have a few examples of container applications that are also using Rust-vmm, such as libkrun and Dragonfly Container Image Service. So you might wonder, since these workloads are fairly different, what is Rust-vmm doing? What are the steps that Rust-vmm is doing in order to enable all these kind of different scenarios? And we are mostly counting on two design principles, as we call them. So first of all, Rust-vmm is working hard to enable multiple implementations. And for that, we are really insisting on building clean interfaces. And these interfaces need to be able to have multiple implementations such that they can be useful for multiple VMMs. And I'm going to give you an example here. So if we take VM memory is a component that is providing a way for configuring and accessing the physical memory of a virtual machine. And it has, in order to do so, it exports a public interface, which is called guest memory. And also, VM memory offers a default, let's call it implementation, so a backend for this interface, which we are calling guest memory mmap. Now, Firecracker, which is one of the virtual machine monitors that is consuming Rust-vmm, is using the VM memory interface, but they have their own custom guest memory implementation, and that is because throughout 2020, Firecracker has been adding support for snapshotting, and for snapshotting to be done, they needed to make some adjustments to the VM memory implementations, which are later going to be upstream. The other thing that we're trying to do with Rust-vmm is that we are trying to have components with at least a dependency as possible. So the components should not really depend on each other. They only depend on each other when they need to. And not only that, but also whenever there needs to be a dependency between components, this dependency will happen at the interface level. So I will give you two examples here. We have the Linux loader, which is a component that essentially loads kernel images into the guest memory. And because of what it needs to do, it needs memory abstractions. So for that, it depends on VM memory. But the catch is that it does not depend on the VM memory implementation. It just depends on the VM memory interface. Another example is the Virtio device crate. This one is essentially providing an implementation of Virtio devices. And by the nature of them, the Virtio devices need to communicate with drivers. And the devices are the ones that are implemented in the VMM, and the drivers are the ones that are in the kernel guest. And for this communication, in order to have this communication, they are using shared memory. Hence, the Virtio devices do need some memory abstractions in order to provide this communication. But again, the Virtio devices do not depend on the implementation. They depend on the VM memory interface exclusively. So if we recap a bit, we have components that we have Rust-vmm components that depend on each other, but they only depend on the interface of them. And then this enables separate products such as Firecracker and Cloud Hypervisor to all consume the same set of devices, but also provide custom implementations where these are needed. And now we are going to take a look at a demo of how we can actually glue these components together and how you can actually build a laser-focused VMM. And the workload that we will want to isolate right now is going to be an HTTP server, and we'll see more about it in the demo. So what we are going to see in this demo is going to be, on the left side, we're going to start a virtual machine that is only going to have a network device configured and is going to be a busy box. So in this virtual machine, we are going to have a HTTP server already started, and it prints reInvent. Now, what we want to do is just upload a image. So let's look at the image that we want to upload. It's going to be called demo. So this is the image that we are uploading. We are going to use a post request in order to upload it to the server. And now we are going to check that the image was properly uploaded, and it was. So we can find it in the virtual machine, but also if we do a GET request, we are going to see the same image pop up. Cool. So now, because we actually started a virtual machine with only a network device, so no storage, what will happen is that when we are going to shut down this virtual machine and we are going to restart it, we will no longer actually see the photo that we uploaded. So let's try to get the photo again. And now when we're trying to open it, it will actually say that it cannot load the image. And the reason is that the image is no longer found, because once we turned off the virtual machine, all the storage is gone. So nothing is in the virtual machine anymore. It starts from a clean state. So, but if we do want to actually have storage as well, what we can do is create a new VMM process where we are also configuring a block device, so the storage. And we're going to essentially go through the same process again, but this time instead of starting a busy box, we are going to use a full blown Ubuntu image. So we have the same HTTP server running, and we are also going to upload the same image again, and the image is now uploaded. We are going to check that it was correctly uploaded to the VMM after a few tries and errors. Yeah, so there it is. And now let's see what happens when we are actually going to do a reboot. So when we're doing a reboot and then restarting the virtual machine, because we are using the storage, now the image should be present after restart. So let's just check this scenario as well. And now when we are opening the image, it should be exactly what we uploaded before. So it looks like it works. So now let's look at what we actually saw in the demo. So in the first part of the demo, we were looking at an HTTP server that only had a network device. So in order to build a VMM with only a network device, what we did is that we took a few components from Rust-vmm. So we took the VM memory with its backend. We took the Linux loader in order to load the BusyBox into the virtual machine memory. And then we took from virtual devices, we only took the network device and some of the VM and vCPU abstractions that are available in Rust-vmm. And to actually build the VMM, we only had to write some glue code in order to make these components work together. And also, we rewrote an API. So what you saw as the command line parameters that we passed, that's the API. And it was just really, really minimal. And these are the only things that are VMM specific. And everything else is consumed and can be consumed from Rust-vmm. But the truly interesting part is that when we wanted to make our VMM more complex, so basically also adding storage, we just had to do very few changes. So instead of only consuming the network device, we also consume the block device. And then in our nothing else changed at all. And on the VMM specific code, we just had to write a bit of code in order to also initialize the block device, and then again a bit of code in the API in order to configure the block device, the storage, via the command line parameters. And if you're wondering why this is important, is because it is enabling building virtual machine monitors that are laser focused much faster than you would if you would just have to write it from scratch or maybe fork something. And all these components in Rust-vmm are battle tested by multiple virtual machines that are running in production right now. And now I would like to invite Samuel to present such a virtual machine monitor that is using Rust-vmm in order to provide isolation for workloads.
Thanks a lot, Andrea. I'm Samuel. I work on a project called Cloud Hypervisor, which is a VMM that's one of the main Rust-vmm crates consumer. And today I'm going to talk a bit about Cloud Hypervisor. And right now I'm going to do a short demo of Cloud Hypervisor. And the goal of the demo, as Cloud Hypervisor is based on Rust-vmm, but aims at running different workloads than the VMM reference or Firecracker. Cloud Hypervisor basically is trying to run more generic cloud workloads from containers, but also regular distribution, Linux distribution, and even Windows images. And the demo I'm gonna show here is basically Cloud Hypervisor running a Windows Server image. We are trying to think about the right workloads to show the whole spectrum of workloads that a Rust-vmm-based VMM could run, and we thought that a Windows Server image is kind of the at the extreme of that range in the big legacy VM workloads. So this is what I'm going to show today. Let me start a demo. Okay, so on the right side of the screen, on the right side of the screen, I'm running Cloud Hypervisor, and on the left side, I'm just starting the RDP into the Windows Server. So, okay, let's start. So here we see I'm launching Cloud Hypervisor, and I'm passing a weird kernel name. This is ovmf.fd, which is actually an EFI firmware. So I'm not launching a regular kernel, but just it's a UEFI firmware that I pass as a kernel path, and I'm using a Windows Server 2019 image, a little tweaked to support Virtualization devices. I'm going to boot with 4 vCPU, and as you can see, there's a KVM Hyper-V on flag for the vCPUs. That means we needed to tweak the vCPU support to also have some special cases for Windows. On the left side of the screen now, I'm launching an R desktop client into the guest. And now you can see, well, that I'm going to log into a Windows guest run by Cloud Hypervisor. So again, this is all running on top of the Rust-vmm crates. And there's a few interesting things that we want to see on this demo, especially on the device model side of things. If we look at the devices that this guest is seeing and running, as you can see here, basically, first of all, it's an ACPI platform. So we need to expose all our device topology through ACPI. And the devices, like the block device here, for example, is a Virtualization device. So we use Power Virtualization from Cloud Hypervisor into the Windows guest. Same for networking adapter. And we also have a random number generator Virtualization device again. So this is Power Virtualized. And last but not least, CPUs. As I said, we started 4 CPUs, and well, we're seeing all those 4 virtualized CPUs here. So this is a completely Power Virtualized device model, and we can even properly shut down this guest here. Here it goes. Everything shut down properly. And so again, the goal of this demo was to show that based on the same set of fundamental crates that, for example, the VMM reference runs, you can take those crates, put them together into something like Cloud Hypervisor, and run not only containers but also all bigger, much bigger, and more PC-centric workloads like a Windows Server. And as I'm showing here on this slide, we're using roughly the same set of fundamental crates as the VMM reference. We're using the same memory crate with an mmap backend. We're using a Linux loader, but not for loading a Linux kernel. Again, as shown in the demo, we're using the Linux loader to load an ELF binary, and this ELF binary is actually an EFI firmware that will boot as a guest and then loads the Windows image. The Virtualization devices are almost the same as the VMM reference one, except we added the RNG, which is a random number generator Power Virtualized device. And we're using the KVM abstraction crate from Rust-vmm again. Some part of this VMM also have specific crates. We have our own VMM glue code. Obviously, we need to put all those crates together into this glue code. We have an API that talks to this glue code and expose the VMM to the user and the tenant. But we also have a couple of interesting crates that are absolutely mandatory to run something like a Windows server. Windows expects devices to appear on the PCI bus, and also expects the platform to be an ACPI one. So we had to add the PCI crate and an ACPI crate to Cloud Hypervisor to support something like Windows. And we want to actually contribute those crates back to Rust-vmm and make them Rust-vmm crates as well for others to use and build specific VMMs. And talking about sharing crates and upstreaming crates on Rust-vmm, what are our future plans with that project? So we want to be adding a few very interesting virtualization components. The first one are very much I/O centric, around storage, networking, and a few others. Mostly based around VirtIO. So we want to be able to contribute and add a block networking and VSOC VirtIO devices into Rust-vmm. But also we want to add the vhost-user-backend crate, which is actually something that's currently a work in progress. And the vhost-user-backend is basically a way to run a VirtIO device and emulate VirtIO devices, but with an offloaded backend. So that brings more flexibility, more modularity, and also to some extent more security, because you can have a privileged separation between your VMM and the actual device backend. To support something like Windows, but also to support other platforms than x86-64 or ARM64 that we currently support as well, we're going to add a vCPU abstraction crate. And again, the ACPI crate is something that you need for a bunch of legacy or regular VM workloads like Windows or things like Ubuntu that do expect a platform description through ACPI. Another thing, interesting thing that we want to contribute to Rust-vmm is an hypervisor abstraction crate. Right now, Rust-vmm is very much centered around KVM. But in the future, we want to support Microsoft hypervisor and potentially other hypervisors into Rust-vmm. So we want to abstract this into a specific crate, which is going to be the hypervisor crate. Andrea mentioned the GPU workloads, and to use those GPUs into your guest, you need two things. You need to be able to pass those workloads through, and for that you need a VFIO crate. And this the VFIO crate support, addition to Rust-vmm is already a work in progress. So this is something that we currently working on. The VFIO ioctl crate has actually been merged very recently. And also to expose those GPUs, all of them actually run on top of a PCI bus. So you need to emulate the PCI bus to be able to, for the guest to be able to see those GPUs. So those are the major components that we want to add to Rust-vmm in the short term and maybe a longer term for some of them. The other thing that we want to improve through the Rust-vmm project. Two things actually, security and testing. The goal of Rust-vmm is to basically is really to be able to run virtualized workloads and in the cloud or in any other vertical. And the idea is to be able to document the threat model that we're trying to address. We haven't done that yet, and this is something we want to do in the upcoming month. Another interesting aspect of Rust-vmm is that it's very much it has a granular design. So we really try to put each and every component into its own crate, and we really try to make it isolated components as much as possible. There are pros and cons to that approach, but definitely one pro is that that allows us to do a very laser-focused fuzzing and integrate fuzzing into each and every of those components, continuous integration. So this is also something we want to start doing in the next month as well. Another thing that we want to integrate into the Rust-vmm components continuous integration is performance testing. We want to be able to assess if adding new features to those components actually triggers performance regressions or not. Okay, so how do you get involved? How do people contribute to the project? How can people help the Rust-vmm Rust-vmm project moving forward? There are two ways. The first one, obviously, is to contribute to Rust-vmm. And you can either add new virtualization components. If you think about a new virtualization component, if you identify gaps into what the Rust-vmm project tries to cover as far as virtualization goes, and there are probably many gaps in there currently, I'm sure. Sorry about that. If you think about a new virtualization component to be added to the Rust-vmm, then the best way to do so is to start a discussion on the community repo on Rust-vmm, open an issue, and start the design discussion for this new virtualization component. Then, once there's an agreement on the relevance and the design of this new component, maintainers will create a repository and set up the CI for this new repo, and people can start contributing to it usually in an incremental way. We're not looking at the perfect first contribution, so this is a very much incremental process. Eventually, when things are settled down and we reach a satisfactory point, things will be published to crates.io. And you can also contribute to existing components. We've created a few labels there into the existing components, a few GitHub labels. Good first issues are the issues that are relatively easy to tackle, and they're very good entry point into the project. There's another set of labels for the existing components, the ones that are looking for help. So some components need help to move forward. They need expertise. They need code contribution, and this is something that has been labeled through the help wanted tag. And finally, there's also some issues in the existing components that need an owner. Some of those issues don't have an owner. They're not being tackled down right now. So if you're feeling up to the challenge, then feel free to own them. Another way to contribute to Rust-vmm is to actually use it. You can basically take the existing crates from Rust-vmm and create your own VMM for any kind of usage that you would have, and you can basically create a laser-focused VMM for the specific needs that you would have for your virtualization problems. You can use the VMM reference as a starting point. That's a really good starting point. Or you can mix and match the existing Rust-vmm components into something that's very customized to you and start from scratch from the existing components. And if you're looking at which of the components are production ready or which one are not production ready, this is something that we've documented in the community repo on Rust-vmm. And we also have an organization, crates.io, that are basically listing the crates that are production ready. And last but not least, if you want to get in touch with us, we have the mandatory Slack channels. Feel free to join and discuss with us on anything you would like, any help that you would need joining the project, contributing to the project, or using any of the crates. We're here to help. And if you're not a Slack fan, which I could understand, you can also get in touch via email with us, and we have a mailing list for this around here. And this is something that we monitor, and we'll answer to your request there as well. Thank you very much. If you want to reach out to us, feel free to use those emails address over there. You can use them to reach out to us directly. And thanks again.